Welcome to Chapter 9 in our Earth Science course. I am sitting in front of Skogarfoss. Skogarfoss is one of the more dramatic waterfalls in Iceland, and we're talking about groundwater and running water today, so I thought this would be an appropriate backdrop for us. You can see how large it is by judging the people up here on the observation platform at the top. There's a trail that takes about half an hour at a fairly steady clip to get all the way up to the top up here and then back down again. So if you ever go to Skogarfoss and are on one of the package tours, jump off the bus and run up there as fast as you can, because they usually only wait for an hour and you could miss the bus if you don't make it back down. And I have gone up to the top there before. I decided to spend the night in Skogar. Foss means waterfall, so Skogarfoss is the waterfall near Skogar. And Skogar is a bustling burg of a town with all of 200 people at most. Despite that, it has a couple of hotels and a couple of restaurants because all the tourists come to see the waterfall here. If I move away a little bit, you can see all the people at the bottom there, and just you can gauge how tall this thing is. It is quite dramatic, and it's mostly glacier runoff that's happening there. So without any further ado, let me get to our sharing of the screens, and let's go on to our slideshow here, running water and groundwater. And I have another picture of myself near the base of the waterfall here. Now the waterfall doesn't look nearly as tall here, but that's because I'm in the foreground. That is at least 2 football fields away. It doesn't look like it's that far away, but that's how large this thing is. Getting any closer than this essentially means you get drenched. So lots and lots and lots of powerful water that's coming off of that. And of course, that's mostly fresh water with a little bit of minerals mixed into it from the terrain. But it's melted glacier, so it's going to be fresh water rather than seawater or salt water. So we're going to talk about all of these different things, which we sort of put in the wording as the hydrosphere. And we'll look at all the different ways in which groundwater and running water shape our environment along the way. You've learned the water cycle before. Water evaporates. It goes into the atmosphere as water vapor. It precipitates and begins to rain back down, or snow or sleet. All of these things are precipitation. It sometimes does that directly back into the oceans and the lakes, but as often as not, it will do so over the land masses. That can do it over plains and over mountains. Mountaintops, of course, will tend to get frozen water at the top. That's why they have mountaintop ice caps even at the equator. Most water on our planet is actually in the oceans. And so the runoff from the continents typically ends up mostly back in the oceans. So there are different things that are involved in the water cycle: precipitation, rain, snow, sleet, evaporation, infiltration, runoff, and evapotranspiration. We'll talk about each of these things as we're going along. But the balance of the water remains in our planet pretty constant. We might have the occasional water vapor molecule float off into space, but not really, because it doesn't typically get that high in the atmosphere. So water is recycled over and over and over again along the way. So we have evaporation, as I mentioned before, precipitation, transpiration, that's going to be coming out of the plants. And then we have infiltration, which is how water seeps into the ground, seeps into the soil, typically to well back up again in lakes and streams and rivers. The amount of water that remains on the surface really depends upon a lot of different things, some of which are no-brainers, like the slope of the land. If it's flat, it's going to stay there. If it's angled, or if, like Skogarfoss here, you're hitting a big break you're going to lose a lot of water along the way. Vegetation will hold on to the water. But we also have to account for the nature of the surface material. Will it absorb things? Will it let things puddle? Will it encourage things to run off? And then, of course, the intensity and duration. When it says rainfall here, we're including things like snow and sleet as well. Running water is really attributed to the sloping of our continents. If you look at the Mississippi River, which runs all the way from Minnesota all the way down to the Gulf of Mexico in Louisiana, you would see the continent of the United States actually tilted over that sort of 1,500 mile or more stretch, depending upon exactly where you want to start measuring from up north, that it tilts all the way down. The Nile, which runs for much, much longer than that, runs along the tilt of Africa, which tilts into the Mediterranean. So the Nile is one of the few rivers actually in the northern hemisphere, and water from the southern hemisphere actually does drain into the basin for the Nile River, but it's one of the very few that actually flows to the north rather than the south. Most of the things, if you think about rivers in the United States, the major ones, the Ohio, the Missouri, the Mississippi, they're all flowing towards the south. Even the Wabash River in our own state, typically, I mean, you'll have branches where it will flow in a more horizontal, latitudinal way, but mostly they flow south. This is because of the way things are sloped, and we have divides. So sometimes you'll have water going in one direction and one in the other, depending upon the terrain. Sometimes those divides can be really subtle, because if you have just a small little hump of a hill rather than a huge mountaintop, the water is still going to break in the different directions as a result of that. And we have rills and we have gullies, which are different structures that are formed as these things are running off. One of the things that happens, of course, is we have erosion, the sediment that is going to be driven off with the water. That will in fact deposit at the end here after it's transported down. So it's produced up here in the highlands, it transports down to an area where it gets deposited. And these areas of deposit can sometimes be quite large. Half the state of Louisiana, including the entirety of the city of New Orleans, is on one of these deposit zones here. That's all stuff that has over time washed down the Mississippi and the Missouri and the Ohio rivers. We have networks that we can see. Networks will sometimes go from the top, well, let's look at B here, that it can go from the top of a mountain off in all the different directions. We call that radial. We can have a branching system that follows the terrain that looks a lot like sort of veins and arteries in your blood. We call that dendritic. Then we have a rectangular pattern that can be based on different kinds of rocks, and we've studied rocks that tend to chop away, break away at angles like this before, so more like a piping system. And then we have the trellis, which seems to incorporate some stronger bedrock, like we might have up here, stronger minerals, as well as weaker rocks along the way that would be more dendritic. But we have those two things combined in that. So those are four of the common ways in which things are drained. Then we have stream flow. Some rivers flow really fast, some go really slowly. If you're sort of in the Mississippi area, if you go to the Mississippi area around the state of Iowa, it tends to go at a nice speed, but not too terribly fast. By the time you're getting down to Mississippi itself, though, the Missouri and the Ohio rivers have both fed into the Mississippi, and it's increased in its speed. And we have a song that even talks about the mighty Mississippi River. In Iraq, we have two main rivers, the Tigris and Euphrates. Those of you who know your Bible know that this is often called the Fertile Crescent, and the earliest cities in the world grew up around here. And they're two of the rivers that are mentioned in ancient texts. One of them, the Euphrates, goes rather slowly and gently. That's the one that everyone chose to live around. The Tigris tends to go really fast and choppy. So it's harder to do business around a river that might overtake your city. It's harder to have drainage and irrigation come off a really fast running one. So it depends on a lot of things, including the shape and the size and the slope. The Tigris, for example, starts out at a higher elevation and flows further, whereas the Euphrates is much more of a flat thing. The Nile River is also a slow running river for the most part, and pretty gentle most of the time. And each year it overflows its banks and then recedes back into its stream, its main riverbed. But when it overflows, it leaves sediment behind, and you can grow things. That's where people have lived literally for thousands of years doing that along the way. We call the amount of water coming off of this the discharge. And here we can see some of the largest rivers, again, in North America, the United States. The St. Lawrence River is mostly in Canada, but part of it borders on the United States here, so we'll call it an American river as well. You can see the Mississippi River starts up here in northern Minnesota. So why it's not called the Minnesota River? Well, and why it's not called the Louisiana River? Long story. The Ohio River, you can sort of see it feeds into it. The Tennessee River mostly flows to the south, but it takes this jog up to the north here and then joins into the Ohio and then into the Mississippi River. The Missouri River as well. The Columbia River is the other river over here that does not join in to the main network of rivers throughout the central and eastern United States. Then we have the Yukon River. Of course, the Yukon is a Canadian territory, but the river originates there and goes through, its longest portion is actually in Alaska. So we have huge amounts, but notice the discharge. Notice how much it is, the Mississippi that we have here overpowers all of them. And the St. Lawrence, which is going out from the Great Lakes here, is also a very strong, powerful one. The Ohio and the Missouri rivers, we would say, are sort of midline kinds of rivers in terms of comparison to the Mississippi. And the Tennessee River is really a gentle river for most of its traversing through the territory. When we're looking at this, we have what's called the longitudinal profile. We can look at it in a cross section. We can look at it from the source or the head of the river and going all the way down to the mouth or the base of the river. And we can see a different kind of section here, how much higher up it is. Here in Indiana, for example, we're several hundred feet above sea level. If you go to Denver, we're several thousand feet above sea level, mile high, 5,280 feet. There's Mile High Stadium there. So the Colorado River, which cuts out the Grand Canyon, is a strong river because it starts from a much higher elevation. So one of the things that we see is we have a higher elevation where it starts. That will affect the velocity, the speed, as well as the amount. We have different things that we can measure when we are looking at rivers. We can have the different kinds of sizes and flow, and flow velocity, which is the speed. The discharge is the amount that we have here. We also have the slope and the roughness. That makes a difference because, in fact, if you have water that's just going over something flat versus water that's going over things that are choppier, the choppiness will in fact impede what's happening. When we have more running water, we talk about erosion quite a bit. We see that at work in lots of places, including here in Indiana. Erosion takes place from rainstorms, it takes place from snowstorms. Then we also have transportation. You can even notice this if you have a strong enough flow of water from rain in your own driveway or your own parking lot. You'll notice that lots of dirt and debris. People who have gravel sidewalks or gravel driveways or other kinds of things like that often have to have that redone periodically, because the transportation of the material will occur over time. So as things are moving along, we have some things that are dissolved in it, but some things that bounce and move and slide along the way. There are particular names for those kinds of things: saltation, bed load. If you want to slow down a river, you can put down things like this. Then we have our dissolved and suspended stuff. Dissolved stuff you won't really see. You might taste it, you might smell it, but you're not going to see it. Suspended stuff, you can sort of take a cup of water and you can sort of see it in there. We typically call both of these things impurities as a sort of generic term. Transportation, again, we have how much it can move. It depends upon how large and what's happening in the river itself, how large it is, as well as the speed of it. So we talk about competence and capacity. Capacity is how much it can take. It's related to how much water there is, the discharge. Competence is, will it move something that big, that big, that big? Will it actually tumble boulders over? Those are part of the load. Then we have sediments, alluvium. There's the talk of alluvial plains. That's basically areas that have built up from the sediment of the deposits that are happening from this. One of the things that happens in a deposition, a depositing, is that this is sort of the end of the line for the river, and it begins to drop its stuff, usually right before it's entering the sea or the ocean. So here we can sort of see a chart that talks about the transportation versus the deposition. Then we have different ways in which things can move around. And this is interesting, not just on Earth, but we see this on Mars. Understanding the way these things work actually helps us to understand where water might have been on Mars once upon a time. We have our bedrock channels. Remember, those are often square kinds of things cut into the rock itself by the water. You run water over something long enough and it will happen that way. We have alluvial channels, which is sort of gentle flow typically, but a widespread flow. Meandering streams tend to go back and forth. Some pictures of the Martian terrain have streams that go almost sort of like snake-like. There isn't water there now, but wind doesn't move like that. Water moves like that. So they look like dried up riverbeds to us. And of course, when we see dried up riverbeds here on Earth, like here's Earth, here's Mars, hey, they look very similar. It's not 100% convincing. Lots of things in science rarely are 100%, but it's very, very close and it's compelling. And then we have braided streams, which are those complex networks of channels that sort of look like sort of brain neuron networks, or the blood flow in our bodies. Here's a braided stream image. You can sort of see all the stuff. There is a general direction to what the flow is here, going from one portion to another. And I don't know on this picture whether it's coming from the top to the bottom or going from the bottom to the top. But essentially the entirety of the terrain, you can sort of see how things are sloping down from both sides in any case. It looks like it's fairly slow moving. If this were faster moving, it would in fact overpower a lot of this stuff. So braided streams tend to be pretty slow. The base levels tend to be the lowest point at which things can go to. We have two general types. We have the temporary area, the temporary base level. Like here in Indiana, there might be a temporary base around Lake Monroe because all of the areas around Lake Monroe are higher than Lake Monroe. So it's not really going anywhere else except through, because it's an artificial lake, where it's been built up to do that. But the ultimate lowest level, base level, is sea level. All rivers run to the sea. If you have watched Finding Nemo, you'll remember that. All drains run to the sea. And of course, make sure you're not in your plastic bag as you're going towards there. One of the things that of course happens along the way is, because water can carry things along with it, it can build up and build up and build up, and it can build up dams, and it can push away things that are in its way if it's flowing. So there are changes in the flows of rivers. The larger the river, the greater the capacity for it to change, but not always greater tendency to change. So here we can see what happens. This is essentially how we built Lake Monroe. They put up some dams. They also had to build up a couple of areas to make sure that the basin area was going to be contained. And we do release things out of the dam. There are a couple of other lakes in the area that do that as well. One of the interesting things about Lake Monroe is there is a town at the bottom of Lake Monroe. Many of the parts of the town were removed before it was flooded in, but it was, in fact, there was a town. So I might offer you an extra credit thing. I'm going to try to remember to do this. Let's see, I'm going to write this down right now. So put extra credit, town at the bottom of Lake Monroe. I showed a video on this town to Beltrace, where I'm chaplain, and everybody loved it. And I would mention the name of the town to you, except that's part of what I want you to do for extra credit. Find out the name of this town and find out what the group of people who used to live there still do. That's an interesting thing too. So I'll be sure to put that up in an extra credit board for you to do for our class. When we look at rivers and streams, we'll often find them in valleys. The Grand Canyon is just one of the greatest of these. But what's happening here, of course, in Skogar Foss behind me, is the same kind of thing that's happening in Yellowstone. The river at the top in Skogar Foss, it's coming off of a glacier. Some in Yellowstone is old glacier water as well. But what's happening there is it's welling up at the top, but it reaches a point where it crushes down and we get a waterfall. And that begins to cut through the mountain system. Notice how rapid this is. We actually call them rapids because this is a fall. This is being pulled by gravity at work here. And gravity is at work down here too, because this area is going to be at a lower elevation than this area. May not be much, may only actually be a couple of feet, but by the time you've got the gravity pulling the water down from the waterfall and the force of that pushing down, it's cutting through the rocks quite dramatically. The valley will widen over time. That's what's happened to the Grand Canyon. That's what happens to a lot of these kinds of processes. And we end up sometimes with a broad valley floor. Sometimes we end up with a very narrow V shape along the way. One of the things, again, you can see in my photo of Skogar Foss is it's got the rather wide floor. Alluvium, the water, it all hits with a great force, but then it's essentially flat. We're almost at sea level at the bottom of Skogar Foss. So what's happening there is the water is at not only the local base level, but also the ultimate base level. And the ocean's actually just a few stones throw away in the opposite direction. So it flattens out and it starts going very slowly. It meanders. It becomes an alluvium or a floodplain. What we also see sometimes with the rivers is that over time, they will widen and widen and widen, and those areas become very, very good for agriculture. What's happening at Skogarfoss is this is all volcanic. The whole area there tends to be volcanic, so there's not a lot for agriculture, but there's some for grazing of sheep. There are quite a lot of sheep in that area. One of the reasons why people want to build around rivers is not just for the water, but because the area around the river has been treated over time to become a good source of agricultural soil. And it's hard to beat that when it happens naturally. One of the things we can sort of see is the changing terrain along the way. Here we have the Colorado Plateau as the river sort of goes down and cuts into it. And then we have different things that will happen with the deposits. We have deltas, which are these areas at the ends of the rivers. The Nile Delta, most of the people in Egypt historically have lived in and around the area where the river meets the sea, the Mediterranean Sea. And that's a huge area, supports hundreds of thousands, if not millions of people agriculturally, as well as in terms of living there. We also see that natural levees can be built. You don't often want to rely on those too much in terms of building your house by them, because just as they have been built up over time, they can be torn down over time. And then we have our alluvial fans, which are similar to deltas, except that they tend to be not at the mouth of the river going into the sea, but in different areas within the landmass, like the one here at Skogarfoss. So here we can see a delta. The river is flowing towards the sea. Well, once upon a time, it was sort of flowing out, and it would just sort of get a little bit further and further and further out until something at some point begins to block part of the flow. So it goes in a different direction, and then it gets sort of blocked again and blocked again, because stuff is floating down and it's going to change its course over the course of time. Deltas are inherently unstable. They're also right at sea level, sometimes even a little bit under sea level. So that's why New Orleans, if you remember 15 years ago, I want to think, we had massive hurricanes, and even though they built up these massive artificial levees, the water still came over and flooded most of the city, because at high tide, the city is below sea level, below the natural level of the sea. So when we're looking at these kinds of things, you need to take into account the overall flooding. Like this, you don't want to build your house and farm in the middle of here if during the flood stage, if that happens all the time, you're going to be out of luck for your house. You can build up levees. There are some natural levees that might be built up over time from that, and they may get further and further up. You would, of course, in this kind of setting, want to build your own as well to keep the water from flowing over. But this is exactly what happens in the Nile, as I mentioned before. The river overflows the banks, but each year, as things recede, it leaves behind a fresh layer of sediment that is very fertile, and people can grow on these. So floods are very common. Weather and human interference are the two main things that cause this. We can do flood control dams. We can try to run the water off in different directions. That's called channelization. And then we build artificial levees. Again, New Orleans, we can see how that doesn't always work so well. Non-structural approaches include just knowing where to build and not build. Here in Monroe County, I lived in a house over in Ellettsville for several years, and it's sort of halfway up a hill. You sort of drive down the hill, and there was this nice little house, very tiny, almost one of those sort of small homes kinds of things. But someone had built it there, and a couple had moved in from St. Louis. And I was going by, and one day all their furniture was outside and they were selling it. I said, well, what's going on? They said, well, we're moving away. This house was built on a floodplain. And every time it rains, all the water comes down the hill and pours into our basement. And even though it doesn't flood into the first floor, the water in the basement is saturating the rest of the house. That was a bad plan for that house. And so they were moving away. And that house is still there. So if you're in Ellisville looking for a house and that one's for sale, don't buy the house at the bottom of the hill. So we also can sort of see here in Indiana and also in Illinois and Kentucky and various places in the Midwest, things like this happening every now and then. The banks of the Wabash, the banks of the Ohio, the banks of various rivers will overflow, and sometimes our terrain is so flat it takes a while for things to drain off, especially if the land itself is already saturated with water. There's only so much water that can be absorbed into the ground because that water has to go somewhere as well. So the New Madrid floodway, we're living not too far here from the New Madrid fault line. You may have felt an earthquake before. I'll talk about that in a later lecture. But when we're dealing with those kinds of things, we have lots of subsurface water. That can come and go as well, depending upon climate and weather patterns. This is the largest freshwater area for human beings, is the subsurface groundwater areas. It's not the largest area of water in the world, but it's the largest freshwater in the world for us. So we have sinkholes and caverns. Here in Indiana, we get lots of karst topography, which is basically areas that have been hollowed out by water flow of one sort or another. So when we look at freshwater overall, again, this is just freshwater. This does not include the oceans here. Notice how much of it is locked into ice sheets and glaciers. That's Greenland, that's Canada, that's Iceland, that's Antarctica by far, and a few other places, Alaska, Siberia. Groundwater is about 30%. So when we're sort of dealing with that, fresh water on the surface is only a small percentage of that groundwater stuff. So when we're talking about lakes and soil moisture and other kinds of things, including water vapor in the atmosphere. So we're talking a very small percentage there. So we live on a very thin sheeting of water. So we do have underground zones of water. Some places are more damp than others. We have what are called zones of saturation, which is it can't take any more. It's completely saturated. The water table can rise or sink. If it rises too much, that's when you get those farms that are flooded because the water table is full. That's the upper limit of the zone of saturation. So we might see here where we have some different water areas that are being, and this is called aquitard, which means it's sort of retarding, and that's an okay word to use in this context. It's, so don't write to my boss and said he used that word. It's okay to use in this context. It's retarding the water from saturating any further because it's a denser or thicker material. So we get a welling up of water here where we might be able to sink a well. Over here, obviously, we don't have that. The water has sunk down to the main water table. But as we notice the terrain going down, the river is at the main water table level. And all things are flowing down to that. That would be our local base level along the way. So how water gets distributed depends upon how porous it is. That's what this means, porosity. And you're probably familiar with that. Some paper towels are more porous than others. Some towels are more porous than others when you're drying off, getting out of the shower. And some will absorb more water than others. And then we have permeability, whether or not it can transfer through one place to another. And an aquitard is something that retards the aqua. It retards the water from going further. So it becomes a more impermeable thing. Clay is pretty good at that. Harder rock can be really good at that as long as there are not too many cracks in the rocks, because the cracks will let everything flow through. And an aquifer is an area where the water essentially just sort of flows on through. Fortunately, most of the ground in our area would be aquifer areas. We can actually do demonstrations, we can do labs. We may actually do a lab like this, where we put different kinds of rocks and soil samples and other kinds of things in a beaker and see how much water will actually fit into that. Of course, if you put in big chunks, you can put in more water. You put in sand, you can put in actually less water because the sand takes up more of the volume along the way. When you sink wells, you're actually lowering the water table. Now, that can be replenished if you have enough rain and melted snow and other kinds of things. But then we also have artesian wells. If any of you are from Martinsville, you may recognize this name, artesian wells. This is water that's higher than the initial groundwater, and it's confined with one of those aquitard structures. So artesian wells, you get a different kind of water, often spring water. Will come out of this. So that's one of the things that happens near Martinsville. Part of that may be because of the previous ice age. The last glacier system to come down into Indiana stopped right around Martinsville. When it retreated, that's why the terrain north of Martinsville is really flat. It didn't reach down here to Bloomington and parts south, so that's why it's all sort of choppy and hilly and rocky. You may notice as you drive north, the further north of Martinsville you get, the flatter things get. The further south towards Louisville or Evansville you get, the more hilly and sort of rocks and rills. So that Martinsville is one of the breakpoints for that. So if any of you are from Martinsville, now you know what artesians are, apart from just being the sort of high school mascot kind of thing. We can also see under the surface, sometimes what will happen is things will become sort of over drilled. This will happen with oil, this will happen with water, this can happen with a number of kinds of things. But if you have a huge draw on the water table, it can actually dry up nearby wells. One of the things that was happening, still happens occasionally, is something called slant drilling, where say I own this farm over here, someone else owns this field over here, they put a well over here, and then they drill down at an angle and start to take away the things from my area. There's some places where that's not legal. There's some places where it's not found out until it's too late. But that makes a difference. That makes a difference. Here we can see an artesian system. We have up here a non-artesian well, because what's happening is the water is actually just sort of flowing from our rainstorm area with a sloping elevation. We can call that the recharge area. But down here, we're pretty much at the base levels for things. And at the base level, this would be confined to the top of an aquitard, and it's sort of between two layers of that, as you can see. So we've drilled through that to get to the water. That would be considered an artesian system. Sometimes water is hot. We get geysers. We get hot springs. That will typically be because we have lava systems, magma systems. Lava systems if they're very near the surface, magma systems if they're a little deeper, but they will typically be hotter if they're hot springs than the air around them. So that can be quite nice. Geysers will boil the water, so you don't want to actually sit in a geyser. That's Old Faithful is known as Old Faithful because it on a regular basis, not like clockwork, it's not every 60 minutes or every 55 minutes or everything. There's some variation in there. But on a regular basis, you can count on it sort of, I think at least once every 90 minutes it'll go up, and then sometimes it'll go up more frequently than that. There is a geyser actually called Geyser in Iceland. That's where the name comes from, Geyser, that goes off every 5 to 10 minutes, sometimes every 2 or 3 minutes, just depending upon what's sloshing around underneath along the way. So this is a picture of Old Faithful here. I will try to remember if I can put up a video, if I can find a video of the geyser from Iceland that I've taken when I was there along the way. There are different problems that we can deal with. This is a renewable resource in a sense, but we can overutilize it, especially because it's not like the sun. It's not there every single day. Rain comes and goes. Sometimes we have more and sometimes we have less. We also have land that will shift around, especially if you take the water out. Let me go back to this area here where we're looking at the cone of depression. It would not surprise me at all if, because of this high capacity well, the land began to sink in that area because partly the water was holding it up. And then we also have contamination. Things run off into the water. And that's a real issue in industrial sites, because what happens, of course, is the industrial waste sinks into the water. Well, where's it going to go? It's not just going to stay right there. It's going to spread out among the rest of the water. Again, Martinsville has had that issue that it's been dealing with for many years. Bloomington had several issues with that as well from the old Westinghouse plant, where they literally just dumped battery acid types of stuff all around the area. So we can watch as water has been taken out of the land, things going down, down, down. Notice how far down the land, the overall land sort of elevation has sunk just over 50 years. And that's largely because they've been using the water underneath to grow things on top, but it keeps going down and down and down and down. This is also a very earthquake prone area, so there's a lot of instability already built in to this area. So if we're looking at the different kinds of aquifers, notice if we have one here that is, we have very rapid kinds of movement. Here we have very slow kinds of movement here. One of the things that we might want to do if we were living in well water in the yellow house here, we might not want to be downstream from our brown house's septic system, because what comes from the septic system, not good stuff. And if it's flowing really fast, you're going to get some of that in the well water that comes up there. Whereas if things are flowing rather slowly, and the septic system is situated above the water table, that's an important function or an important consideration here as well. So the stuff that comes out of the septic system takes a while, and soil actually is a cleansing mechanism, and rock and sand and other kinds of materials that the water flows through will actually be a purifying system, especially over time. So groundwater usually has just a little bit of acidity to it. You can talk about the pH level of waters. It does dissolve calcite in limestone. We end up with caverns formed, and we have that here in southern Indiana, and going into Kentucky and other things, you can go see caverns that are formed, and we have stalactites and stalagmites. Stalactites are hanging from the top. Stalagmites are growing up from the bottom, and those are common features from dripping water. So they're called dripstones. Here we can sort of see this is a pretty typical icicle, but here we have our stalactites and our stalagmites. I remember when I was learning to play the piano as a child, I had to learn, of course, the left and the right hand. And I had a piece that was called stalactites and stalagmites, and you had the upper and the lower as stalactites and stalagmites. So that's how I learned that, pretty much. And then we have good old karst topography. Karst farm park. We have sinkholes, we have caves and caverns. This will often happen when water sort of wells up and builds up in different areas. One of the issues with our own campus at Ivy Tech in Bloomington is that the karst topography might actually still exist under our parking lot, under our campus building in different ways. You can't guard against it 100%. They've done a really good job at taking the water away. That's why we have the lake just north of our campus, and we have, you may notice, the sort of the drainage stream that goes by around our parking lot. So they've done a good job, but sinkholes happen. So beware, because we live in the area, especially on the western side of Bloomington in Monroe County, karst topography. And what happens, of course, is we end up with sort of water flowing. We don't have any grand canals or canyons like this along the way, but water will well up in different ways and will create these areas that used to contain water, but no longer contain water because the water table has sunk along the way. And that is it for chapter 9. So I will see you for chapter 10, and I will put up something for the town at the bottom of Lake Monroe.